Hey everybody, welcome to InterviewBlog. In this video, we'll be covering the insertion sort algorithm. So the question gives us an array of integers and it wants us to use insertion sort algorithm to sort the given input array. So insertion sort algorithm is a very easy algorithm, but it is not very efficient technique to sort a list of numbers. In insertion sort, what I will do is I'll be maintaining a tentatively sorted list in the front of the array, and each time while I traverse the elements of the array, I'll be adding these elements into the tentatively sorted list. So let us now see this example. So initially, I will consider the first element of the given input array as the tentatively sorted list and the remaining part of the array as unsorted. And considering the tentatively sorted list with the first element of the array because a list with one element is considered to be sorted. So now I'll be traversing the remaining part of this array. So I'll be reaching this 2. Now my tentatively sorted list contains 8 and I'm going to insert this 2 into the tentatively sorted list. So what I will do is I'll compare 8 with 2. Since 8 is greater than 2, I'll be swapping 2 and 8. So my tentatively sorted list will now become 2 and 8. The remaining part of the array remains the same. That is 4, 9, 5 and 1. So now my tentatively sorted list is 2, 8 and the remaining part of the array which is unsorted is 4, 9, 5, 1. So now I'll be picking up this 4 and I'll be inserting this 4 in the tentatively sorted list. So first I'll compare 8 and 4. Since 8 is greater than 4, we'll be performing a swap and our tentatively sorted list will now become 2, 4, 8. So now I will compare this 2 and 4. So while comparing 2 with 4, we can see that 2 is less than 4. Hence, there will be no swap. So our tentatively sorted list is now 2, 4 and 8. And the remaining part of the array is 9, 5 and 1. So now we'll be inserting this 9 into the tentatively sorted list. To do that, we'll be comparing 8 and 9. Since 8 is the greatest element that is present in the tentatively sorted list, we'll be comparing 8 and 9. So we can see that 8 is less than 9. Hence, we don't have to swap anything. So now our tentatively sorted list becomes 2, 4, 8 and 9. And the remaining part of the array is 5 and 1. So now we will try to insert this 5 into the tentatively sorted list. So to insert 5, we'll initially compare this 9 with 5. So we can see that 9 is greater than 5. Hence, we need to swap 9 and 5. So the tentatively sorted list becomes 2, 4, 8, 5 and 9. Now we need to compare 5 and this 8. So while comparing 8 and 5, we can see that 8 is greater than 5. Hence, we need to perform a swap and our tentatively sorted list now becomes 2, 4, 5, 8 and 9. So now we'll be comparing 5 and 4. While comparing 5 and 4, we can see that 4 is less than 5. Hence, we do not need to perform any swap here and our tentatively sorted list becomes 2, 4, 5, 8 and 9. And the remaining part of the array is 1. So now we need to insert this 1 into the tentatively sorted list. Now I'll be comparing 9 and 1. We can see that 9 is greater than 1 and hence we'll perform a swap. So after performing the swap, our input array would be 2, 4, 5, 8, 1 and 9. Now we have to check the elements 1 and 8. We can see that 8 is greater than 1. Hence we need to perform a swap and our tentatively sorted list becomes 2, 4, 5, 1, 8 and 9. Now we need to check 1 and 5. We can find that 5 is greater than 1. Hence we need to perform a swap and after swapping our tentatively sorted list becomes 2, 4, 1, 5, 8 and 9. So now we'll be comparing 1 and 4. We can see that 4 is greater than 1 and hence we need to perform a swap and our tentatively sorted list becomes 2, 1, 4, 5, 8, and 9. So now we need to compare 1 and 2. Since 2 is greater than 1, we need to perform a swap, and our tentatively sorted list is now 1, 2, 4, 5, 8, and 9. Now, since we have traversed the entire array and we have inserted all the elements into the tentatively sorted list, it means that we have completed our insertion sort algorithm, and the final array that we get after inserting all these elements is our answer. So this is our insertion sort algorithm. So hope you understood the problem. Let us now analyze the complexity of our solution. So the best case time complexity of our algorithm tends to be big O of n, and the average case time complexity of our algorithm tends to be big O of n square, and the worst case time complexity also tends to be big O of n square. The space complexity of our algorithm tends to be big O of 1 in best, average, and also in worst case. So why is the space complexity constant? Because we are not using any extra data structure. The tentatively sorted list is maintained in the same original list. So we don't use any extra space, and our space complexity tends to be big O of 1. So the time complexity of our algorithm tends to be big O of n in best case, because in the best case scenario, when the given input array is already sorted, we'll be traversing each and every element and we'll be comparing that element with the previous element. Since the particular element is already greater than the previous element, we'll be traversing the array only once. So our best case time complexity tends to be linear. The average and worst case time complexity tends to be big O of n square, because for each and every element, we will be traversing the tentatively sorted list from the last and will be positioning the current element in the tentatively sorted list. Hence, this takes a time complexity of big O of n square. So hope you understood the problem. Let us now implement it in code. All right, so we got our insertion sort function defined, which takes in an array. So in insertion sort, we are going to maintain a tentatively sorted list in the beginning of the array. So I'll be traversing from the second element of the array. That is, for I in range 1, len of array. So each time I traverse, I'm going to have a variable called j, which is going to have my ith index, and while j is greater than 0, and array of j minus 1, which is the previous element, is greater than the current element, which is array of j. Whenever this happens, we need to swap the elements that are present in the j minus 1 index, jth index, and we'll be passing in the array. So after swapping, we need to decrement the jth index. So I'll be writing the swap function above. So def swap, which takes in two indices I, j, and an array. So inside the swap function, I'll be saying array of I, array of j is equal to array of j, array of I. So after this traversal is completed, we will be returning the sorted array. So I'll be saying return array. So this is our insertion sort algorithm. So this algorithm has a time complexity of big O of n in best case and big O of n square, that is n into n, in average and worst case. And since we maintain the tentatively sorted list inside our array, our space complexity tends to be constant, that is big O of 1. So hope you understood the problem. So in best case, our time complexity tends to be big O of n. This is because whenever the given input array is sorted, we will be traversing that array using this for loop, and for each and every element, this while loop will never get executed, since in a sorted array, the previous element will always be less than the next element. So we'll be traversing the array only once using this for loop, and hence our time complexity in best case tends to be big O of n. Let us now test our solution. Let's say our array has 8, 2, 4, 9, 5, and 1. So we'll be saying print insertion sort of array. So let's run our solution now. So we have got a sorted array here, that is 1, 2, 4, 5, 8, and 9. So let us now test another test case. This is a sorted array 1, 2, and 3. So in this case, yes, we are getting a sorted array 1, 2, and 3. So let us test another test case 3, 2, and 1. In this case, we are getting 1, 2, and 3. So our solution works fine. Hope you understood the problem. Do subscribe and check out our channel for more videos. Thank you so much.